particular example, I have to confess, I don't even know if I can claim that one technique's better than the other. Well, maybe I should back that up.
So,
You know, I'm the one who made a silly arithmetic, or a simple algebraic mistake, miscounted my exponents. So maybe getting rid of radicals was maybe the easier approach. I don't know. It's up to you.
so is there any situation where you would get a different volume using the two?
Absolutely not. But like I said before, maybe using one approach you get something that you cannot integrate
Okay.
with the tools in your back pocket. Yes.
Like,
Sir.
what would that
So
be?
if you were to rotate the same thing on the y-axis, you use the washer method, but integrate there's a y.
No, that's a good point. If I were to rotate, you said about the y-axis?
Yeah.
I'll put my pen down, no writing. If I were to rotate this region about the y-axis, am I going to integrate with respect to x or y? Depends on which method you use. Let's use the washer method.
Y.
I'll get a dy. Let's use the cylindrical shell method.
X.
Definitely the dx. Are you there? Bradley, did I answer your question? I'm sorry.
Well, I was just wondering, like, what a situation would be where you couldn't integrate it going through, you know, either the shell method or the washer method, and it would actually force you to use one or the other.
Couldn't you have one of your functions be like sine x or something, and then when you do it with cylindrical shells, you get like x sine x?
I think that's a really good one. I was thinking of something different. But I think yours would be shown on the board. If I were to revolve that about the x-axis, can I avoid drawing the picture? You're just going to get a
Circle.
a
Or,
football.
yeah.
And I compute the volume using the washer method. Well, using the washer method, I think I get pi times the radius squared. You guys, I just want a yes or no answer. Can you handle that integral?
Yes.
I think the answer is absolutely yes. Piece of cake.
One minus cosine 2x.
Gosh, isn't that quick and easy? Yes, sir.
Where did the pi halves come from there?
You know, in my head, I skipped a step. In my head, I was evoking my double angle identity for the sine, for the cosine function. It was saying another name for sine squared of x is this over 2. I pulled a 2 out. That's all I did. But if I were going to compute the volume of the solid of revolution, this football, if I can call it that, using the cylindrical shell method, then I think I've got horizontal rectangles. And I have to rotate those about the horizontal x-axis. Now, would you guys not agree? I'm going to get inverse sines times the radius, which is y. I think in the integrand's position, I'm going to get things like y's times inverse sines of y's. And I can't handle it.
Okay.
Well, I'm sorry. I meant to say, this week, I can't handle that integral. This week. We'll be able to handle it with something called, if you've seen this, integration by parts. We're just not there yet. You guys, do you think I've given you enough examples to start running with this? Do you think? I hope so. I hope so. If I have, can we do this? And can we do this? Do you guys think you can speak for me? I may be saying something you've never seen before, but to start my conversation up,
Divide it into n sub-intervals.
subdivide this interval from A to B into n subintervals. Isn't this all old business? Maybe even consider an arbitrary I subinterval. Maybe even discuss the last subinterval. Now, if I project up to the curve, am I not going to generate these 2 points right here? They are going to be x of I minus 1, f of x, I minus 1, and is this one over here going to be my x of I, comma f of x of I? You guys, I want to concentrate on that I subinterval. Do you mind if I blow it up? And I'm blowing it up. I think I get this. X-axis, y-axis. Here's my x of I minus 1. Here's my x of I. I forget what my curve looks like, but here's the point x of I minus 1, f of such. And here's my point x of I, comma, f of such. What I want to do is approximate the distance from this point to this point. And I think an approximated distance, what I'm really doing is approximating the length of the arc along my curve over that I subinterval. But because I'm approximating the length of that black curve with a red linear expression, or a red linear line segment, then I think my life is going to be this easy. It's going to be as easy as looking at the Pythagorean theorem. Because I think in connecting horizontally to vertically, I am generating a nifty little right triangle where here's my right angle. And I think that this length right here in green is going to be nothing more than a small change in the x direction. Oh, by the way, are all the delta x the same? Yes, I'll keep them as such. And I'll think of the vertical blue length as a small change in the y direction. I gotta confess to you guys, in my picture, even though from A to B I regularly subdivide the interval, those corresponding changes in the y direction aren't going to be the same. Can I call this delta y sub k? And I think, with my red pen, I'm going to think of that red length as nothing more than a small change along the curve over the k subinterval. I said k. I don't know why I call it k. Can I call it I? That's what I really meant. My apologies. I'll be consistent with my index variable. And clearly in that picture, certainly is the case that by the Pythagorean theorem, small change along the curve, along the I subinterval, squared, is going to be the sum of the squares of the other lengths, which in this case are going to be delta x and delta sub y sub k. Delta of y sub k. I keep using k's, I don't know why. I'm so sorry, you guys. Thanks for keeping me straight. Or shall I say this? I think an approximation for the change in length of the arc over the I subinterval can be interpreted as a square root sum of these two squares. Just that if I so choose, I can suggest that delta of S of I could be interpreted this way. Oh, did I just make a mistake? Yeah, I think I committed a huge algebraic blunder. Technically speaking, what I was trying to do is pull out a factor of delta x, but this is what I got as a ratio. But if I pull out a delta x squared from the radicand's position, doesn't that show up as a delta x on the outside? And now if I were to sum together, all these delta S of i's, as I range from 1 to n, take the limit as n increases without bound. I think what that's going to allow me to do is compute the exact length of my curve, the value of the arc length along my curve, as x ranges from a to b. And rewriting the limit of that Riemann sum as a definite integral, I think it clearly becomes nothing more than the integral from a to b of the square root of 1 plus, oh, look at that. As delta x goes to 0, I'm going to have to put n equals infinity. Doesn't that mean I'm just dealing with the first derivative function? Squared. And of course, I'm integrating with respect to variable x. Now I gotta confess, sometimes it's difficult to anti-differentiate with respect to variable x. Sometimes I might do this instead. At this stage of the game, let me pull out not a delta x squared, but a delta y squared. And I think a small change in for s, at least over the isomerical, could be interpreted as such. It's just that here too, if I take a limit as n goes to infinity, which means delta y goes to 0, then I think the length of my curve could be interpreted as nothing more than the valuation of the integral from somewhere to somewhere of the square root of 1 plus, well, my function g is derivative in terms of x, and I'm going to integrate on this with respect to y, and I'm going to integrate with respect to the variable y. Just a different way of looking at it.
You lost me at L equals.
Because I skipped too many steps. Let me verbalize what I did. You know, when you look at the symbol right here, I think all this really is the length of the hypotenuse of this multicolored triangle, which I think approximates the length of the curve of black. I just maintain that as delta x gets closer and closer to 0, the length of that hypotenuse in red gets closer and closer to the length of the black arc. Oh, but shoot, you guys, this isn't going to work. That's simply over the I subinterval. But now if I sum together all those values and take the limit as n increase not bound, I can rewrite the limit of that Riemann sum as a definite integral.
Okay.
And I'm just using a different letter, big L, for the length of the arc. I don't know why, to be honest with you. It's because what we typically use. Maybe it's not the best, most appropriate letter, but it's L for length.
When you take the limit of the delta x and the sum of
Yes.
delta x into y, are you not just approximating a tangent line?
You know, I think this is very different from a tangent line. If you want to consider some kind of line, you should consider a secant line, because I'm actually passing through 2 points in the curve. I'm not just tangentially touching the curve. But it's
But if you take the limit, aren't you taking the points infinitely small to where you get this, you know, at the infinite part, you get an actual point, no?
all right, I see your point, no pun intended. But that extreme is sort of like I no longer have 2 points to discuss on, I guess.
I got you.
I think it's more appropriate looking at it this way. I think. You guys, let's put this to practice. By the way, with the squaring in the integrand's position, this makes my life miserable. You know, for me to sit down and write questions where I can actually come up with an integral that's integrable is actually rather difficult. You open up any calculus text on this discussion of arc length, you'll find the examples not quite numerous as you would in other sections for other topics. It's really difficult to write examples for which these integrals are integrable, because it's group business. But I'd come up with a few. So everybody, question. Can you and I compute the length of the arc along this curve f over the interval from 0 to 1/4? Well, if I'm going to use that first integral right here on the very bottom column on the left-hand board, I'm going to have to come up with a derivative function for f. So differentiating, I get this. Which means to compute the length of that arc, I'm going to divide the integral from 0 to 1/4 and square root of 1 minus that derivative squared. And I'm going to integrate with respect to x. this is a nice example of Harry Potter mathematics, where addition magically turns into subtraction. Sorry. Either way, I guess I'm gonna have to clean things up a little bit. Is that the integral from here to here? Is that the square root of, is that a 1 plus 4e to the 4x? And I'm integrating with respect to x. Yes, sir.
So on the integral on this board over here, is the dx under the square root, or does it?
No, sir, I really did not mean for it to be. Remember how I pulled a delta x all the way out of the square root of this process?
Okay.
That's why my delta became a dx, but certainly not under the integral.
Okay.
Excuse me, certainly not under the radicals.
Okay.
Gosh, you guys, I'm stalled. What do I do next? I said, gosh, you guys, I'm stalled. What do I do next?
Turn the square root into 1/2.
I might have to use a U-sub.
Yeah, turning it to 1/2 is no problem. Using fraction exponents. I think eventually I have to use a u-sub. And so committing to a u-sub, let's see how it works. If I allow u to be equal to the square root of 1 plus 4e to the 4x. What does it say about du?
I don't think you can do that.
I just did.
Well, I mean, you did, but you don't have an e to the anything on the outside, and you're going to be left with an e to an exponential dx.
Wouldn't it just be u equal to 1 plus 4e to the 4x?
What about
The whole square
2e
root
to
of
the
x
2x?
Well, can I just twist your arm? What would du be? 1 over 2 root stuff. But times 2 at the inside. But that would be a 16 e to the 4x. But divided by 2, would that give me 8 of these things?
Yeah, that doesn't help.
Which means in the integrand's position, I've got the integral of, well, root stuff has another name of u. But another name for dx, if I were to isolate dx, if I isolate dx, I have to multiply both sides by root stuff, which is just u, by the way. Times, well, 8e to that power. Let's see what 8e to that power is in this equation. I think another name for 8e to the power is just going to be 1 over 2u squared minus 2. I've lost it. I've lost my du. I also lost my bounds of integration. My bounds of integration are merely going to be, you guys aren't going to help me, are you?
Well, why is it a 1 over
1 over 1.
2u squared?
Well, if I divide both sides by 8e to the
Oh,
4x,
I
I think another name downstairs for 8e to the 4x is twice that. But my bounds of integration, you guys help me. Is that a, ay, ay, ay. Is that a root 5? Root 1 plus 4e. I just lose my arithmetic skills today, sorry. Now, is this nicely integrable? That was a question, you guys. Is there anything I can do? Yeah, what's the thing I can do? Add. Come on, you guys, what's your favorite number to add? What's the easiest number to add to anything? 0. So if I add my funky looking form of 0, don't I get this? Come on, you guys, I want some honesty. Is that okay? So, everybody, let me stop. Let me put my pen down. No writing. I want a yes or no answer. 100% absolute piece of cake to anti-differentiate? Yeah, just get a U. What about over here? Someone said yes. I think for many of us, the answer is going to be yes, because I knew that a lot of you are coming in here from other universities. So for those of you not looking at this book or not being raised from this book in Math 30, you probably would have distinctly said, to anti-differentiate, just don't even write. Just write down the answer as a I'll sit down. It sounds like it's going to take a while. What was that? Inverse.
Coding.
Inverse. Hyperbolic tangent?
Well, that's not.
Yeah, I know, it's
We
not
haven't
fair
learned
to
that
you,
yet.
those of you who are raised through this particular calculus text. And I know sometime this semester I have to give a better discussion of hyperbolics, but for those of you coming from the outside, raised with the Stewart technique or Larson technique, many other authors, you've seen these hyperbolic functions before and you've actually anti-differentiated them. And you could have said inverse hyperbolic. Now, I'm not going to embarrass you with the question. How many of you have already taken Math 31? So it was just more than a handful. For those who have already taken Math 31, if you don't remember hyperbolic tangents, don't worry about it. I meant inverse hyperbolic tangents. Don't worry about it. You can easily commit to partial fraction decomposition, whatever that is for the rest of us in class. Don't worry, you'll know in the very next chapter. We're getting there. For this first example, though, I really wanted to see if anybody was going to give me the answer, inverse hyperbolic tangent. I guess for the rest of us, we can't finish. We don't have the integration techniques, but we set it up and clean it up as much as we can. So now can you give me an
So-
example where we could finish?
On a test this week, if we don't get to partial fraction decomposition yet, but if we've already gone through that, can we use it?
Yes, you can. Of course you can.
Cool.
But the only reason, Bradley, why I really posed this
Yeah.
question for today, I want to see if anybody in this room can give me inverse hyperbolic tangents for anti-differential.
Okay.
How about then? Oh, you guys, there's plenty of time. I feel like I don't even have to rush. That's so nice. How about something like an x cubed plus 1 over 12x over the interval from 1 to 2. Question. Let's you and I compute the length of the arc along this curve as x ranges from 1 to 2. So let's set up our integral. Of course, when I set up the integral, I do need the derivative of this function somewhere along the way. Can we just take our break before we set up that integral? Can you get the derivative? You guys tell me if I'm wrong. But that means the length of my curve along the values of x from 1 to 2 is computed by looking at the integral of the square root of 1 plus the square of that derivative. But you guys, this isn't going to work if you're not awake. So we're all awake. Okay. You said it, we're all awake.
You said it.
Let's use a tad bit of color. How about a Christmas color? Does this give me 9x to the 4th plus twice the product of these two, which actually is a minus 1/2? Is that a plus 1 over 144x to the 4th? But that gives me the integral from 1 to 2 of the square root of, well, combining the first and third terms and using my other Christmas color. Doesn't that give me this in green? Now, be clear with me. Is that going to be a piece of cake, the anti-differential? No. Really? Because I see I got the integral from 1 to 2 of the square root of an absolute perfect square. What's the perfect square?
3x squared plus 1 over 12x
Squared.
squared.
Did you guys see it? Yes.
Where'd you get 144x squared?
Yeah, it should be four.
It's x to the power above.
In the green,
From red to green.
in the green, 144x.
So what do you say?
Yeah, where it's in the green, it's x squared. That's why
Yes,
I thought it was
X
a.
to the 4th. See, look.
Oh, okay.
But you guys see my point. Look what you see in red. That was already a trinomial equivalent to this perfect binomial square. And what you see in green is the same darn trinomial with a sign change in the second term. It's just cheating. I know for free that this trinomial is equivalent to that perfect binomial square, but with a sign change in the second term. But now that I got the square root of something squared and everything's positive over there, I think I have the mathematical legal right to make the proclamation that this is nothing more than the integral from 1 to 2, well, just a 3x squared plus 1 over 12x squared. And I'm integrating with respect to x. But that merely gives me, I don't know, you guys, what does that give me? Is that an x cubed? Is that a minus 1 over 12x? Evaluate from here to here. Or does that give me an 8 minus 124? Minus 1 plus 112? Well, now it's just a matter of arithmetic, isn't it? Actually, you know what I subtracted? I think it should be 169. But you guys can double check my arithmetic. That will be the exact length of my curve, assuming I have no silly arithmetic errors along the way. Guys, any questions? None? Alright. How about this? I got 15 minutes. I can so easily come up with one more example where we can finish it well within 15 minutes, and then I'll stop talking. And even if you don't want to finish, that's fine too. I don't like my examples, the first two, because I never really incorporated this particular interval. So, allow me to make one up. Can I raise? So, third and last question. Consider this equation. Because the integral necessarily involves a derivative of my function g, everybody watch my writing. I made this example up out of thin air. Didn't I do a terrible job? I really meant to say x is equal to stuff. My apologies. Let's differentiate. I think dx dy is going to be nothing more than 3 halves y to the positive 1/2 pound. Which means picking this up off the inkboard, using it for g prime of y, slapping in the radicand's position, that gives me the integral from my 1 to 2 of the square root of 1 plus the square of whatever this derivative is for x with respect to the variable y. But that's going to give me the integral from 1 to 2 of the square root of, gosh, you guys, I'm hearing my voice too much again. What's it going to be? 1 plus, how about 9/4 1? Assuming you're falling into a very deep sleep, tell me how the heck I'm going to actually guide this integral. You guys, really?
You could just use u sub
A very quick use.
very easily. Yeah.
You're simply going to have a linear relationship between u and y. And paying the consequence, doesn't that mean this? Now, committing to the substitution, doesn't that allow me to rewrite as such?
Pull 4/9 out.
You know, I really can't, you're right.
Yeah.
But in the end, doesn't that just simply give me a root y, a root u, du? It's just that the coefficient that gets pulled up in front is gonna be my 4/9. Well, you know what? That really is easy to anti-differentiate. That gives me 4/9 times u to the positive 3 has power. Whoops, I forgot my coefficient. Is that times 2/3? Need value from here to here. But that merely gives me my 27ths times 13/4 raised to the 3/2 minus my 13/2. Do I have those backwards? I think I do. Upper bound, lower bound. You guys, it's getting too sloppy. Do you mind if I stop? That'll be the exact length of that curve as y ranges from the position of 1 to positive 2. Seriously, you guys, this isn't too bad, is it? I mean, I can't make these that complex with these particular intervals.
So where did we get 13 by 2?
You know what, sir, you can double check me. I was just simply changing my bounds of integration. For example, if y holds a value of 1, correspondingly, doesn't u hold the value of 1 plus 9/4, which is 13/4. That's where I got that value. And I played the same game with positive 2.
I think it would be 11 by 2.
You know what, you're right, I just checked it in my head. Oy, oy, oy. So you guys, I can't do any arithmetic. 3 becomes a 1. I'm so sorry. I do indeed stand corrected. But it's the idea, the approach, the method, okay? It is. Let's see how we can get some practice. You guys, I don't know if you've dove in here and counted, but you know, for this semester, the summer session, expect me to come to class and approximately just cover one section a day. It's not bad. I mean, there's going to have to be a few days, just a few, where I cover 2 sections in one day. I promise I'll do things like I did today. Where one section, like computing arc length, isn't going to take us that long to generate a few examples. I just thought it was a light section. I thought today was a good candidate for me to slip in 2 sections of the text. Well, to set you guys off, section 6.1. Take a peek at these. Then take a peek at these. Now do it.
Are you gonna pass back the quizzes?
No, I didn't get them done yet. Oh, by the way, I've got some time just right now before I leave this room. I'm going to post the solutions, which I forgot to post. I do have them.
So can you post the other quiz that you did as well?
Yes, all of them. Since it quiz 1, I've been taking that super long. I just keep forgetting to post it.
So, Professor, the quiz we gave, that was number 3.
It was.
So are we gonna have a quiz tomorrow?
Yeah. It's just over the material.